All right, we'll take a look at 51 here. You recognize this kind of reaction?
I do.
What's this? AgNO3?
That is silver. No, that's a aqueous solution. I'm guessing it's a nitrate.
Silver nitrate solution.
Yeah, Teresa, silver nitrate.
A solution.
Solution and
Potassium chromate
so
solution.
this is AB. So we're going to form silver chromate and potassium nitrate. That's what we have. Driving force, the chromates are insoluble except for group 1 and ammonium. So this precipitates. How many milliliters of 0.650 molar potassium chromate are needed to precipitate all the silver in 415 milliliters, 0.186? So this is a limiting reagent problem. We're just given the milliliters. We convert milliliters to liters, liters to moles, and then moles to moles. Moles of product, and then to grams. Actually, or how many milliliters? Okay, to precipitate all the silver. So all the silver, in this case, if you want to precipitate all the silver, then we're going to go from milliliters of silver nitrate to liters of silver nitrate solution, liters to moles of silver nitrate, moles of silver nitrate to moles of potassium chromate, and then moles of potassium chromate to liters. Since we have the molarity here, this is mole per liter. So let's set up something like that. That's what we do. This is, sorry, it wasn't a limiting reagent problem. That's just straight stoichiometry problem. Let's take a look. What's the next one? We have
60.
60. Okay. 60. All right. 60. Do you recognize this pattern here? Mg solid plus 2 HCl's.
Single replacement.
Single replacement. Now, single replacement should work in this particular instance because magnesium is a really good reducing agent. A is the reducing agent. And then this is mineral acid, so H plus is the oxidizer here. And so single replacement should work, and that gives us magnesium chloride and hydrogen gas. A method of lowering the concentration of HCl is to allow the solution to react with a small quantity of magnesium. The problem with this method is you're going to contaminate your solution with magnesium chloride. If that's acceptable, then this method works. How many milligrams of magnesium must be added to 250 milliliters of 1.023 molar HCl? So to reduce it to exactly 1.000 molar HCl. So we need to lose some number of moles. What we could do is we could figure it out. I mean, there are different ways we could solve this. One of the ways is we need to lose 0.023 molar. If we need to lose 0.023 molar and we have 250 milliliters, then we can figure out how many moles we need to lose. And once we figure out how many moles we have to lose, then we can go from moles of HCl to moles of magnesium, and then moles of magnesium to grams of magnesium. So it's a stoichiometry problem with a twist.
So you said HCl was a mineral acid?
Mineral acid, yeah.
There are like
Two types of acid. Yeah. The two types of acids would be mineral acids and oxidizing acids. And the difference is in terms of redox properties. And so, in terms of redox properties, chloride is a reducer, not an oxidizer. However, in an oxidizing acid, the anion, generic acid we call HX. Where X is just whatever anion that we have with it. The cation's always the same, the anion's different. And then what I'm saying is there are two types of anions. One type of anion would be like the chloride, acetate, bromide, etc. These types of anions are reducers, reducing agents. And then you have another set of anions, which would be nitrate, sulfate, phosphate to some extent, but phosphate's not the greatest oxidizer. would be a better oxidizer? Chlorate, perchlorate, etc. These ones are all electron poor. These ones are electron rich. These are electron poor oxidizers. And so these are OAs. These OAs are all stronger. OAs that are stronger than H+.
Mr. Chabot, is that first one supposed to be nitrate?
Yes,
Okay.
thanks. I was thinking nitrate. Yeah, the first one's supposed to be nitrate. Do you see the difference? And so when you have, we have to consider the pattern here in single replacement is that X is always the spectator. None of that's the case. So well, we have to look at certain things like, for example, you know, chloride's not the greatest reducer. Magnesium is a much better reducer. But what if we had something that's more difficult, you know, to oxidize? Then that could change things. And so when we have these types of acids, we can term these the mineral acids. And so in terms of redox, they're all kind of the same. But these ones, in terms of redox, are quite a bit different. And so these would be the oxidizing acids here. And oxidizing acids you have to be very careful with, because you could have a lot of unwanted reactions. So as an example of that, if we used HCl for this, that's fine. However, if we use nitric acid, do you know what else? You know, with nitric acid, we could have the same thing. With nitric acid, H+ is plenty powerful enough to oxidize magnesium. But what's going to happen is there's going to be a competition. Not only does H+ want to oxidize magnesium, what else wants to oxidize magnesium? Nitrate. So if we use nitric acid here, nitrate's going to want to oxidize this. And so rather than producing hydrogen, we're going to produce NOx. And NOx are deadly gases. Hydrogen's a deadly gas too if it explodes. You know. Or a combination of both, you know, hydrogen and NOx.
Oh, that'd be even worse.
Yeah, that would be pretty bad. And so you're going to see plumes of orange smoke come off the graph. You know. And so oxidizing acids aren't so clean. Okay, what number is next?
After
Yeah,
is 70.
70.
Yeah, 61, 66, 70.
Chlorine can be generated by heating together calcium hypochlorite and hydrochloric acid. So let's write the reaction for this here. Calcium hypochlorite. What is hypochlorite?
CLO.
ClO. And the charge on ClO? So we'll need two of those. This would be calcium hypochlorite and hydrochloric acid. We can kind of get an idea of what's going to happen here. Because hypochlorite is the same as bleach. And so this would be a bleaching agent. Sodium hypochlorite is bleach. But this would be bleach as well, because hypochlorite's a bleaching agent. Hypochlorite's a bleaching agent because its oxidation state on chlorine is what? We looked at this before, +1. So And so this bleach can oxidize things. It can oxidize what else is present. Well, would it oxidize H plus? No. Would it oxidize calcium 2 ions? 2 plus ions? No. Could it oxidize chloride? Yes. And there's one more thing it potentially could oxidize. What is that?
The oxygen? I think. Oh wait, no.
The calcium.
What else is in this mixture?
The calcium.
Water.
Oh.
Yeah, it's hydrochloric acid, so this is aqueous. And so there's water. So let's take a look at what we predict for this. Calcium ions, are those oxidizer or reducer? I forgot to put that chart up. All right, see calcium ions over here on the fluorine side. If you look at that chart, I'd use that chart more, but what side is fluorine on? Left side or the right side? It's on the right side. That chart there is good for the activity series because look at the top left. Do you see the activity series there? Lithium, rubidium, potassium, calcium. That's the activity series. That chart there is called a chart of oxidation potentials. And so what happens is you lose electrons going left to right. This chart here is called a chart of reduction potentials. That is, you gain electrons going left to right. It's basically the same chart. We can either use the oxidation potential chart or the reduction potential chart. It used to be the oxidation potential chart was the normal one to go to.
How similar is the oxidation potential in volts up there? It says -2.87 for fluorine. And the valence force for fluorine, how similar are those?
You mean electronegativity?
Yes.
Yeah, they're related. These are related.
Because I know it's 4.
It's 4.0 on the electronegativity chart, right?
Fluorine,
Yeah. That one, we have to reverse it because fluorine's on the, if you look at that one, fluorine's on the product side. So if we flip it and make fluorine on the reactant side, then we change the sign. So rather than negative 2.87 volts, it's positive 2.87 volts. Positive 2.87 volts, the higher the voltage, the more force there is. And so in general, the higher the voltage. The situation with these voltages is this. So the higher the voltage, the greater the force. If you look at this voltage here, it's 0. And that's for H+. H+ grabbing 2 electrons has 0 force. H+ doesn't want any electrons. Like for example, H+ magnesium metal. And the answer is no. Because what is the absolute worst oxidizer in the universe?
Fluorine.
In the universe. Would you say water is the absolute worst?
Oh, no.
Would it be?
That's
Like the H2?
-0.8. Would you say the absolute worst oxidizer in the universe? The absolute worst oxidizer in the universe, would you say Li+? If Li+ were the absolute worst oxidizer in the universe, then we should call this 0. And then we could easily figure out, everything, is going to be better than 0, right? And so all these will be positive. But do you think that's easy to figure out what the absolute worst oxidizer in the universe is?
No.
Because somebody can always think of something worse, you know? It's not that hard to think of something worse. So for example, Li plus would be a pretty bad oxidizer because Li plus has a very weak pull on the electrons. This is what makes lithium metal such a great reducer. It's a conjugate relationship. So if this is very weak, then this is very strong. But I can think of a worse one than lithium ion. Do you know what's worse than lithium ion?
What?
Lithium metal. Lithium metal, does it want another electron to form lithiide ion? The Li minus? Okay, this has got to be the worst. But you know what? I can think of something even worse than lithiide. You know what? I think Li minus would be even worse. Is if Li minus gains another electron, we're going to form Li2 minus. So do you see this is just a ridiculous kind of game? And so what people said was, okay, forget it. What we're going to do is we're going to come up with an arbitrary zero.
Wouldn't Li minus be unstable?
Yes, it is. And Li2 minus is even more unstable. You could actually form Li minus. Li2 minus would be awfully difficult to form because this would go in the next shell. At least the Li minus, this electron would go in this 1s orbital here. And so this is an arbitrary zero. So negative doesn't mean, all of a sudden, these are all oxidizing agents. So this negative, what this negative means is it's 0.125 volts worse than H+. It's just an arbitrary zero. It's like temperature, Celsius temperature. You're at positive 10 degrees. Positive 10 degrees means there's motion, right? Negative 10 degrees Celsius means what? The motion all of a sudden flips? Or what happens to the motion? All of a sudden you're walking forward and then you start walking backward? No. There's just going to be motion and it's going to be less. So minus Celsius is meaningless. It just means it's 10 degrees cooler than an arbitrary zero. And so this is what these negatives mean. There are negatives that actually mean something as well, but these negatives are arbitrary. And therefore, the way we read these is the higher the voltage, the stronger the force, basically. It's related. Pauling did stuff that's related to this deal. So we have calcium ions. Oops. Which are oxidizer. And then we have, we would think that this is, well, an oxidizer because chlorine's not happy. But you know what? Chlorine can become even less happy if it loses more electrons. So if you think about hypochlorite, what would be even worse than hypochlorite? I mean, that is less stable. What would be worse is the chlorite. And what would be worse than chlorite? Chlorate. And what would be worse than chlorate? Perchlorate. And so this is both an oxidizer because it would like to go to chloride, this is happy. And it's also a reducer because it can get worse. It can get worse, and what's the limit? Perchlorate. H plus is a oxidizer. Chloride is a reducer. And water is
neutral or both.
Both. So we picked the strongest oxidizer. What do you think is the strongest oxidizer? Water versus bleach?
Bleach.
Bleach. What do you think is the stronger oxidizer? Calcium ions or bleach?
Calcium.
Calcium ions?
Yes.
So you better not take those calcium supplements. If you take calcium supplements, a lot of people take calcium supplements. That's worse than bleach?
Absolutely.
Absolutely worse than
Yeah.
bleach?
Probably pure calcium might be.
What's that?
Pure calcium might be, but the calcium tablets might be less oxidized.
Yeah, pure calcium metal is dangerous stuff. Yeah, it's pretty reactive because of the conjugate relationship. Calcium ions are actually more stable than sodium ions. How stable are sodium ions? Pretty stable. I mean, people eat these. People eat calcium ions, but would people eat bleach tablets? I've seen these, the bleach tablets for swimming pools. People put that in. But they don't, you know, a lot of swimming pools, they want calcium. Because calcium's a hard ion. You know, they use like sodium, it's probably better. Bleach. So what do you think is a better oxidizer? Calcium ions, which are in your bones, your teeth, or bleach? Bleach. So the strongest oxidizer is going to be hypochlorite. What's the strongest reducer going to be? We have, actually H+. Oh, H+ versus bleach. That's more tricky, isn't that? You know, but what do you think would be less happy? A chlorine in a positive one or hydrogen in a positive one? Probably chlorine in a positive one.
Yeah.
And so we're just going to go with this. Because the problem is bleach on our chart here? No. Unfortunately, bleach is not on our chart.
Oh wait, Professor, go down.
Wait, what's this?
Wait.
Yeah.
I'm sorry?
I think it was at the very bottom.
OCL.
Oh,
The
it
second
is
one's
on our
bleach.
chart. Sorry. Bleach is on our chart. Where should we position it?
Between
0.89.
sulfur and nitrate.
Yeah. So bleach here, hypochlorite ion, is stronger than
Silver.
silver
But weaker.
ions, but weaker than
Nitrate.
nitrate. So it's pretty strong. And then compared to H+, it's a lot stronger.
Yeah.
You guys see that? Okay. Oh, that's good. Bleach is on our chart. I was going to go to Appendix D, but I'm glad I don't have to go to Appendix D. Okay, what's the strongest RA? Now, this is going to be between chloride and water. Both chloride and water are pretty stable. You drink water and you eat salt. So which one do you think? Well, this one, we're just going to look at the chart. And so the strongest reducing agent would be lithium, right?
Yeah.
And now we just go up until we hit one of these. Here we have water, but we're missing,
Cl.
no, what's that called?
That's
Sulfur.
sulfur dioxide?
Sulfur dioxide. These are SOx, oxides of sulfur. Anyway, we don't have SO2. Can't use that. This is hydrogen peroxide. How about this one? Can we use this water?
No.
No, because we're missing, what's this called?
Nah. Nitrogen.
Nitrous oxide? Yeah? Nitrous oxide.
I said NOx.
Or nitric oxide.
Nitric oxide. Nitric oxide won molecule of the year. So you see it here. Nitric oxide. Now here we have water, but it's with iodine. Here, now we have water. And so where's chloride? Chloride's up here. So which one's a better reducing agent? Water or chloride?
Water.
Water. Water is a better reducing agent, but it's harder initially to reduce. This is like this. Do you want to wait? Let's say you can earn an extra $5 if you wait like 5 years, you know, on your deposit. Versus if you want to get out of it quickly, the next week you can earn $3. So if next week you can earn $30, or in 5 years you can earn $5, which one would you pick? Oh, the $5 for sure, because it's more money, right? Would you do that?
No. Because it took too much time.
Time is important, yeah. Time isn't, it's not just the quantity of money, but it's also, there's a time factor. You know what we call that in chemistry? Whenever we look at a chemical reaction, we consider two things. We consider thermodynamics. Thermodynamics is like that $5, you know? That's going to give you the most energy, $5 worth of energy, versus $3 worth of energy. $5, you want that, right? If you're getting it. If you're paying for it, you don't want to pay for it. You'd rather pay for the $3. But we also have to consider kinetics. Kinetics is how long does it take, you know? Is it really worth waiting for? Let's say you can get $4.50 tomorrow, or you can wait 3 years and get $5. What would you rather do? Well, you go, well, thermodynamics says I should go for the $5 because that's going to be the best return, right? But you're totally ignoring kinetics. And so nature kind of does the same thing here. Energetically, which one has higher voltage? Energetically, which one has higher voltage? Now, if we're on the right side of this, and we're going to the left side, what do we have to do to the sign here?
Change it.
Change it. So which one has a higher voltage? Let's take a look at the voltages here. These voltages are called potentials. And so if I take a look at the potential for water here, it's going to be negative 1.229 volts. Okay, negative. Negative is meaningless. It just means lower than hydrogen. And so this is just weaker than hydrogen. Here's hydrogen at 0, so we're below hydrogen. Hydrogen is a pretty good reducing agent. In fact, hydrogen is an excellent reducing agent, and yet it has a 0. All right, and then what's chloride?
Plus or minus 1.358.
Okay, so the difference, is the difference huge?
No.
So we got negative 1.229 volts versus negative 1.358. The difference is huge in terms of time. If you oxidize chloride, all you're doing is you're plucking an electron from the outermost shell. And so you're going to pluck the valence electron in chloride. How hard is that? Well, if you're an oxidizer, you come in and you just take the furthest most electron away. And so here's this electron that's far away from the nucleus, and then you come and take that electron. Right? But if you try to oxidize water, when you oxidize water, what has to happen? Do we just pluck an electron off a water molecule and then we get an H2O plus?
No.
No. If we pluck an electron or electrons off water, it's a bit more complicated because look at, we have to break bonds, and then we got to strip the electrons off the oxygen. And so that requires a bit more work. And so for chloride, it's easy pickings. For chloride, we start off here, say, and then we pluck the electron off. Let's see, chloride's more stable. So we pluck the electron off, and then we're left with chlorine over here. So 2 chlorides, chlorine plus 2 electrons. So plucking the electron off is like this process right here. Boom. But if we start off with water, then the return is going to be greater. That is, it's going to cost less overall energy. This is kind of weird because it's, you know, inverted in a way. And then we end up with 2H plus and O2 over here. And so doing all this bond breaking and everything requires a greater investment here, initial investment. And plugging off the electron of chloride requires a smaller initial investment, but the return here is going to be greater, in other words. These are kind of weird to think about, but there are different ways of thinking about it. And so the other way of thinking about this is like, you know, would you rather invest, let's say, $1,000 to earn, you know, $10 of interest, or would you rather invest a $100 to earn, you know, $8 of interest, something like that? And so what happens is this. We predict this one to be the strongest RA. But chloride turns out to be easier to oxidize. We predict this one to be the strongest RA because it's going to give us the most energy, but chloride's easier to oxidize and it gives us a decent amount of energy. And so this is easier to oxidize, this is what's going to happen first. And so this is kinetics here. It's faster to oxidize chloride than water. And so this is the only exception to the chart that people should know. Otherwise we just use the chart as is. And so the only exception to the chart you should memorize is chloride versus water as a reducing agent. Chloride wins, even though water is a better reducing agent energetically here, or it appears to be. Chloride's the compromise. Since both of these species occur on the chart, then we could just copy the half reactions off the chart. We don't have to generate our own half reactions. Generating our own half reactions is more work. And so here, chloride. If chloride is the reactant, then we're going to take two chlorides, which would be at the top there. And then the two chlorides are going to go to a chlorine plus 2 electrons. So that's this half reaction. And then I'm going to copy the half reaction for hypochlorite or bleach, which is down here. Hypochlorite plus water plus 2 electrons yields chloride plus 2 hydroxide. And then we're going to combine these two half reactions. And we look, I have 2 electrons being lost here and 2 electrons being gained here. So electrons cancel nicely there. And the overall reaction here is just going to be 2 chlorides plus hypochlorite plus water produces chlorine plus, ooh, there's a chloride here. I need to cancel one of these out. Plus chloride plus 2 hydroxides. I'll cancel it out now. And so this chloride will cancel out one of these. And so overall I'm going to get chloride plus hypochlorite plus water yields chlorine plus 2 hydroxides. Then we check, is it still balanced? 1 chlorine, 2 chlorines, 2 chlorines, 2 oxygens, 2 oxygens, 2 hydrogens. It's balanced. And the charge, -1, -2, and then -2. So that's balanced. Then we look for the driving force. The driving force, I like to get off the half reactions here. So if we take a look at the half reaction, chloride is our reducing agent, and therefore chlorine must be our conjugate oxidizer. Hypochlorite is our oxidizing agent, therefore chloride and hydroxide must be our conjugate reducing agent. And so over here, this is our reducing agent, and hypochlorite and water, this is our oxidizing agent. chlorine will be our oxidizing agent in the reverse, and hydroxide will be our reducing agent in the reverse here. So this is kind of odd. This is the chloride. One of the chlorides canceled out, I think. Yeah, this is a bit tricky as far as this goes. So maybe what we'll do is we'll just compare the two oxidizing agents, hypochlorite versus chlorine. Hypochlorite, which we said was between silver and nitrate here, versus chlorine. Which is up here. So hypochlorite, this looks to be weaker, and chlorine looks to be stronger. Do you see that? Yeah? Yeah. And so it looks like the driving force is reversed. And what we'd say is that there is no reaction based on this. Okay, let's go back to the problem here. So they're saying that calcium hypochlorite and hydrochloric acid react. Calcium chloride and water are also formed. Okay. So it depends on the conditions. We do it under standard conditions. And so we could change things a bit by doing this. This is what we would have gotten. We would have gotten this. It depends on how uphill this is. So if we're going from weaker to stronger, you know, is it a small hill or is it a very large hill? If it's a small hill, then what we have is we have something called the dynamic equilibrium curve, and in which there are going to be some population of product here. But a larger population of reactant here. So we end up with partial reaction. If it's a very big hill, then essentially no reaction because the population up here is negligible compared to the population down here. So it could be one of those situations, but when we do Chem 1A stoichiometry, we typically do Chem 1A stoichiometry assuming we have 100% reaction or 0% reaction.
100% reaction.
Yeah, in this case, they're assuming 100% reaction. And how can you do that? Well, there are certain ways we can help drive this. So if we have a dynamic equilibrium like this, what we can do is we can remove some of the population here. If we remove some of the population, that makes more room up here for more to rise up. And so one way of getting this reaction to go is to remove the chlorine. Chlorine's a gas. And so if you can remove the chlorine gas, then that creates more room at the top. And then even though it's not that favorable, you know, we can get this to go to completion just by continually removing the chlorine. That's a trick that you can use in these equilibrium. It's like having a leaky bathtub. You know, or waves. Let's say you know there are waves here, and you have a little pool here, but you keep draining the little pool off to somewhere else, then it's going to refill, isn't it? As the waves are coming in. Yeah. And so it's the same kind of situation. And so there are things that we can do to get it to go, but this is more of a straight stoichiometry problem here. Okay, I was just looking at reactions for right now. We can look at stoichiometry.
For 70?
Uh-huh.
Why isn't it a double replacement reaction?
Okay. question is, why isn't this a double replacement? It is a double replacement reaction because it fits the form AB plus CD. And so this is double replacement. What we'd form is calcium chloride and hypochlorous acid. And then you'd say there is a driving force. You know, we're going from stronger acid to weaker acid here. And so this would happen too. But when we analyze reactions, there could be other reactions that could occur between these, and then we look at which one has the greatest driving force. The driving force of this one's quite good, but when you have bleach, you know, regardless of the form, this is why I call this bleach, but normally bleach is sodium hypochlorite. What the important point is that oxygen's in the +1, and so if I have hypochlorous acid, could I call that bleach as well? Is that going to have bleaching action? Yeah. And so we could have this metathesis, aka acid base. This would be acid base as well. Hypochlorite is a base. But we could also have the redox reaction occur. And so there are multiple reactions that occur in this. If we form hypochlorous acid, it doesn't really change things that much. And so this is something you learn in Chem 1B. You learn about speciation of it. Do you know when you pour bleach, actually not even when you pour bleach, in a jug of bleach contains sodium hypochlorite, correct? But did you know there's going to be some hypochlorous acid in there? Because hypochlorite can attack water. And if hypochlorite attacks water, what does it form? It forms hypochlorous acid and hydroxide. Then we look, you know, is this favorable? And so we take a look. Are we going from stronger to weaker? And so the acid here is water, and the acid in the reverse direction is hypochlorous acid. And I'd expect this to go backwards. And so I would expect it to be in favor over here. But when we look at this, it's not that far uphill. And so what we have is, yes, the population is mainly down here, but there's going to be some population up here, and that some population will be this. And so when we look at the speciation, it's going to be a mixture. So when you have a jug of bleach, it's not just hypochlorite. It's going to be a mixture of hypochlorite and hypochlorous acid and hydroxide in that mixture. In Chem 1B, we deal with those mixtures. In Chem 1A, we don't deal with those mixtures. And so in Chem 1B, we would actually figure out what is the ratio between these, you know, in there. And so a container of bleach, there's other things in there. It's like the same thing. When you go out and buy a container of ammonia, aqueous ammonia, is it just pure aqueous ammonia? No, there's also some ammonium and hydroxide in here through the hydrolysis of water. This is hydrolysis of water too. And how did I get the ratio? I said it was 99% to 1%. Where did I get those numbers? I got those numbers from Chem 1B stoichiometry calculations that you spend a lot of time doing in Chem 1B. And so to make a long story short, yes, this reaction is, you know, this reaction we'd expect to occur for sure. But even though we have different forms of this, hypochlorite and hypochlorous acid, both of these are bleaching agents. So hypochlorous acid, I'd call bleach. Sodium hypochlorite, I'd call bleach. Calcium hypochlorite, I'd call bleach. All those I'd call bleach because it's the hypochlorite, not necessarily what the cation is. It's what the anion is in this case. So they're all bleach. And then the bleach is going to be an oxidizer, and so we look at the redox. Normally we try to keep things simple, but what typically we do is we look, you know, is there a metathesis reaction, yes or no? Then if it's yes, we still look, is there an acid-base reaction? Yes or no. We still look, is there a redox reaction? In fact, in this next lab, experiment 18, we're going to have one that's going to have two reactions that happen. One reaction happens quickly, and that's what you observe first. And then over time, it changes because the second reaction comes in, and the second reaction was a little bit slower, but it had a greater driving force. And so it changed. The product actually changes.
Is that similar to how yesterday you said when you leave hydrochloric and I think acetic out, it turns flat? Or is
no,
that
that's a little different. It's just because those are gases. Whenever you have gases dissolved in water, it can degas.
Okay.
Whether it's CO2 or anything else. Okay, after number 70 comes what?
77.
77.
Oh, 77 is so fun. It's nice.
Okay.
Easy stoichiometry.
Yeah. This always throws people for a loop. If normally we have 2 reactants, but what if we have 3 reactants? Well, we did have 3 reactants, I guess, yesterday. But let's take a look at this reaction here. The C4H9OH. C4H9OH. What's your guess on this?
For the name?
Yeah.
Oh, ISO. For 4.
ISO? Well, where are you getting ISO from?
Is ISO 4? Oh, I almost went wrong.
It could be ISO. There's probably a lot of what we call isomers.
It's an alcohol.
Let's see, how many is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10 hydrogens.
So will be say it will be four propanol?
Well, it'd be bute because we 3 carbons is prop, 4 carbons is bute. Yeah, so it's butanol. But is it 1 butanol or 2 butanol? Can you tell? Or maybe it's like that iso kind of deal. Or it could be something like this. Actually, there are a number of isomers. This is what you do in organic chemistry. You draw out all the potential isomers for this. So for example, could this be it here? Is that C4H10O? C4H9OH? Well, we have C4H9369OH. Right. What would you call this?
C3C3C3COH.
Yeah, this is getting more complicated to name. So this would be like a prop here with a methyl and an alcohol, Or you might call this like a kind of, like isobute, in that case. Or it could be here. It could be the second carbon that has this. And so what we need is, we don't know which one it is. This is one of these. And so this is why the structural formula is much better, because the structural formula will be different for all of these. This would be CH3, CH2, CH2OH. This would be CH3, CH2, I'm missing an H. This should be 4 bonds. CHOH, CH3. And so butanol, 1 butanol, 2 butanol, and this would be quite a bit different. This would be, CH3, and we have 3 CH3s attached to the central COH.
Yeah.
Well, we don't know which one it is, but all of them are going to behave pretty similarly in terms of redox. And so we got C4H9OH plus NABR plus H2SO4. What do you think is going to happen? Well, you might go, okay, this has got to be double replacement here. And so normally a lot of people, what they'll do is they'll just kind of ignore this. They'll ignore the butanol because, and then they'll just go, oh, this is AB plus CD. This is AB plus CD, we're going to get what? Sodium, sulfate, and hydrobromic acid. Is there any driving force there? So we're going from sulfuric acid to hydrobromic acid. Both of those are strong, so there's no driving force there. And then we think about butanol. You know, what do we know about butanol?
That's 4 carbons.
Yeah, is it? Can you burn butanol?
Yeah.
Yeah, you can burn butanol. And so we might have a redox reaction between sulfuric acid and butanol. You know, because sulfate is an oxidizer that we've seen on the chart here as well. So we can go over here and take a look at our chart. I'll put the chart. There it is. Sulfate's an oxidizer here. And so there could be some redox reaction because butanol you'd expect to be a good fuel, and sulfate's an oxidizer, so we could have a potential redox reaction occur here. But there's one other type of reaction I didn't talk about much. Do you know what type of reaction I didn't talk about much?
Combustion.
I talked a lot about combustion, too much. What are the types of reactions?
Metathesis, redox, and acid-base.
Acid-base. And in acid-base, there are 2 types of acid-base reactions. What were the 2 types of acid-base reactions?
Mineral acid.
Lewis and
Minerals and
oxide.
oxidizing acids.
No, those are for redox. Mineral and oxidizing acids are for redox properties.
And what about Bronsted and Lewis?
Bronsted and Lewis. This chart here, is this a Bronsted chart or a Lewis chart or both? This chart of acids.
That one. Bronsted.
This is Bronsted. Did I talk about Lewis? A little bit, but not much, right? Not much. Lewis is important. Lewis acids and bases are taught more about in Chem 1B. So let's take a look at the reactions that they show. The reaction that they show. What number was this? 77. Oh, here it is. You know what kind of reaction this is? Is this a redox reaction? What do you think? Is that a redox reaction? How can you tell if it's a redox reaction or not? Oxidation state. Do you see a change in the oxidation states?
No.
No, I don't either. I don't see any change in oxidation states.
I just see a lot of swapping.
Yeah. So it's not redox. Is this metathesis? No, not metathesis. Is this Bronsted acid base?
No,
No, not
probably not.
No, not really. No.
It doesn't
What do you think? If it's not one of those, it must be
Lewis.
Lewis.
Lewis. And so this is an example of Lewis. Lewis is a bit more complex and more difficult to predict. Organic reactions, you look at something called the organic reaction mechanism, in which you can rearrange the electrons. And so this is an example of a Lewis. Lewis acids are a bit more complex. That's why we like to talk about Bronsted acids and bases, because it's a lot easier to deal with. But anyway, this is stoichiometry, so we just have 3 reactants, and this is a limiting reagent, so we just have one, additional thing to calculate. But we have the balance. Is that balanced? No, that's not balanced. So one thing is we got to balance that reaction, and then we do the stoichiometry for that. Is it balanced? Okay. And I guess we don't have to balance it. All right, what's next? 79?
Yes.
How many grams of commercial acetic acid? Commercial acetic acid is 97% acetic acid by mass. Must be allowed to react with an excess of PCl3 to produce 75 grams of acetyl chloride if the reaction has a 78.2% yield. And so when we look at this reaction, what does it look like to you?
Double replacement. Because the Cl attaches. Yeah.
Yeah,
Actually, no, yeah. Because
Kind of.
Cl attaches to acetic and.
right. So it's kind of a double replacement, but the problem is the other product should be pH3, but the product is H3PO3.
So, could it be a redox?
Yeah. This is a really weird reaction because this was a carboxylic acid, COOH, now it's a COCl. And so this is looking like a redox reaction because here, actually, what is the oxidation state of phosphorus in PCl3? Plus 3. What is the oxidation state of phosphorus in this? So we do hydrogen first.
Oh wait. Plus 3.
Is it plus 3?
Yeah, because hydrogen would be +1, oxygen would be -2, which would be +3 to -2, so P.
Yeah, so did the P change? No, the P didn't change. And then over here, the oxidation states don't change. And you know what? This is not a redox. It kind of looked like a redox because of the oxidation states. But it's not metathesis. It's not redox. Is this Bronsted acid base? No, this has got to be Lewis. And to figure out Lewis acid base reactions, we usually draw the Lewis structures and arrows and all that kind of stuff. And so, I'm gonna do it. But anyway, this problem has a couple of percentages. So, did you guys already do this?
I did this.
Oh, you did it? Okay, how was it?
Brute force stoichiometry.
Okay. Pretty easy. Okay, let's move on then. Move on to 88. Sodium bromide used to produce silver bromide for use in photography can be prepared as shown. How many kilograms of iron are consumed to produce 2.5 times 10 to the third kilograms of sodium bromide? So we have a series of reactions here. And so what should we do? Should we calculate the yield of iron 2 bromide first? Or actually, no, we're starting with sodium bromide. So if we start off with sodium bromide, then where can we go? So I have this equation, once I balance it.
Well,
I could go back to iron 3, this one, whatever this is.
Yeah.
This is mixed. So I can go from NADR to Fe3Br8, and then from Fe3Br8 to this, and from this to this, and then this to this. So I could work backwards over 3 steps to figure out how much. Or I could do this. Oh, I can't. I'm going to have to work backwards. Or maybe not. You know, the strategy here is this is what I would do if I were doing this. I would balance this last equation here. And then I'd figure out the sodium bromide to Fe3O4 magnetite ratio here. And then once I do that, I'll go from kilograms of sodium bromide to grams of sodium bromide, grams of sodium bromide to moles of sodium bromide, moles of sodium bromide to moles of magnetite, once I get the mole ratio. And then I would skip these 2 steps here, and I would say that all the iron in magnetite came from the original iron. And therefore, I get 3 moles of iron for every 1 mole of magnetite. And then that allows me to skip these 2. That only works if all the iron ends up here. All the original iron ends up in magnetite. Do you see that?
Yeah.
And so I can skip 2 steps by doing that. And that's commonly done. Okay, number 92. Oh, actually, let's take a brief look at these reactions. This is an element plus element, redox combination reaction. So iron's going from iron 0 to iron 2 plus, bromine's going from bromine 0 to bromine minus. Okay, what is going on here? This is some kind of oxidation as well. This is iron 2 being oxidized to whatever. This has got to be 3 irons at plus 8. 3 irons at plus 8, I'd say 2 plus 3s and 1 plus 2. You've seen that before in magnetite, right?
Yeah.
Not complete oxidation, but we oxidize 2 out of the 3. And so we'll have 3 irons here to start. And then this is another redox reaction here. Okay. So normally when we do this, we predict complete oxidation, normally. But sometimes it doesn't happen, complete oxidation. Okay, let's go on to 92 here. 92, a mixture of Fe2O3 and FeO was analyzed and found to be 72% iron by mass. So this is another mixture problem. And so what is the percentage mass of Fe2O3 in the mixture? So there are different ways. The 2 most common ways of solving this are system of equations, 2 equations, 2 unknowns, or the what? Graphical method. Now, one thing I need to mention is for test preparation, if we do a problem in class, you want to make sure you can do it, on your own, and that it makes sense to you. If we do a problem in class and it doesn't make any sense to you, make sure you get it cleared up before the test. Make sure you understand what's going on with that. And so we did the graphical method. That's my preferred choice. I would do the graphical method for this. What is the percent iron in rust? What is the percent iron in FeO? And then see which one this is closer to. Pinpoint it by coming up with an equation that describes that relationship. Okay, so that's that's not even an advanced problem. That's one of the standard problems in here. That would be normally it would be considered an advanced problem, wouldn't it? You would think.
Well, now we're going to the advanced.
Now we're going to the advanced problems, which starts with 93. And I didn't assign 93. And so for the advanced problems, I assigned 97. Let's take a look at 97. Hydrogen gas is passed over rust at 400 degrees C. Water vapor is formed together with a black residue. A compound consisting of 72.3% iron and 27.7% oxygen. That's the black residue. Write a balanced equation for this. So this is kind of what we do. It's hard to predict sometimes these, so what you do is you just mix it together and see what happens. So this is an example of a skeleton redox. The skeleton redox is we mix these 2 together, hydrogen and iron 3 oxide. And what we form is a product. We form this black residue, which is the major product, which is a compound of iron and oxygen. And so we'll figure out is the empirical formula of this, and then we'll balance it. Did somebody get the empirical formula for that? What my guess is?
What did you guess, Professor?
My guess is if it's not iron 3 oxide, it's probably iron 2 oxide. My guess is it would be iron 2 oxide. And so if it were iron 2 oxide, then this is the setup. I have hydrogen and Fe2O3 going to iron 2 oxide plus whatever. And so the two half reactions I have is Fe2O3 goes to iron 2 oxide and hydrogen goes to question mark. But we don't have to worry about hydrogen, right? And oxygen. Hydrogen and oxygen are always balanced. We balance hydrogens by adding what? H pluses. And so this one we don't necessarily have to worry about, but they tell us, they tell us already what it goes to. Do you know what it goes to?
Water.
Water. So it goes to water. Okay, and then we balance it this way. Here. That's the way we do it. So this one is actually, seems easier than 92. So I don't know what they're doing here. All right, some more problems to go, but I want to talk about the lab coming up. I'm going to do the lab differently than
The one you just did today? I mean, yesterday?
no. Experiment 18. In experiment 18, you do a whole bunch of redox reactions. So if you take a look at the pre-lab, A is fine, you know, it's a redox reaction. A lot of these are redox reactions, maybe not all of them. Okay, this one, the following reactions have been observed, and so we look at the oxidizer and reducer. The purpose of this lab is to come up with a redox chart. And so you put the strongest oxidizer, they want it down here at the bottom left. Our redox chart has the strongest oxidizer at the top left, but that's all right. And so they're trying to determine the redox chart. How you determine the redox chart, the strength is you just react them together and see what happens. But instead of doing that, you know, and so this is observational. It's observational in the sense that you're going to observe what happens and then rank them according to how they reacted. But instead of doing that, what I want to do is I want to just predict what's going to happen. You know, we already have the chart. We don't need to generate a chart. And so the whole purpose of this experiment is to generate a redox chart like this, you know, here. And so they go on and, okay, here we're going to have a redox chart. This redox chart is not like the one in the book, and it's not like that one. That redox chart has the strongest oxidizer over here at the bottom right. And so this is yet a third way of writing the redox chart. And so they want us to generate a redox chart based on what reacts and what doesn't react. Okay, we're not going to do that. What we're going to do is we're just going to predict the products for these reactions here. And so what I'd like you to do is I'd like you to try to predict the products for some of these reactions that we have here. We're going to start with, let's see, which one? Oh, this has been shortened a bit. We're going to start with this one here, which
The
is
silver nitrate
silver nitrate,
and
iron 2
Two
sulfate, aka ferrous sulfate. Iron 2 is ferrous. So if we have silver nitrate and ferrous sulfate, what forms? Well, that looks like a metathesis reaction, doesn't it? It doesn't look like a redox reaction.
I would say silver sulfate and iron nitrate for double replacement.
It looks like a double replacement, but chapter 18 is not double replacement. Chapter 18 is redox. But it could be both. So you look, is there a double replacement? Is there an acid base? Is there a redox? And so analyze that for all of them. Okay. And then we're going to look at this one, 18Hc. Let me go back up here. So that was silver nitrate and iron 2 sulfate, and then I want you to do this one here, which is going to be not copper and bromine.
Alkali ions and reducing agents?
FeCl3. We're going to do this. FeCl3 plus KBr. And we're going to do this one. HCl plus KMNO4. Okay, so why don't you try those redox reactions there? They all look like double replacement. But are they?